In this today's class, we're going to see about the resonance in the electrical circuits. So basically, there are two questions will be arise. So what is mean by resonance and which circuit this resonance conditions will occur. So normally this question will arise in our mind. So generally, the resonance circuit is a combination of R, L and C elements, and it has having a frequency response characteristics. Normally the characteristics should be like this. Okay, so this is the corresponding frequency and this is the corresponding impedance value. Okay, so that resonance circuit must have both inductance and capacitance because it is a combination of RLC circuit. I already told that. So consider it is a RLC circuit. So this resonance circuit must have this RLC values, but definitely it has some LNC. But this resistance is due to the resistance present in the coil, and some resistance is present in the source itself, and we may add some resistance to the circuit to obtain some particular resonance characteristic shape. Okay, so when resonance occurs due to the application of proper frequency, the energy absorbed by the one element, so here there are two elements is there, one is L and another one is C. As usual, the inductance absorb the reactive energy and the capacitance release the reactive energy in general, so that at resonance condition this inductance will observe the reactive energy which is equal to the reactive energy which is released by the capacitance. Okay, so that in a practical circuit there is some resistance associated with the reactive elements. I already told that this inductance has some resistance associated with it, so that this extra resistance will result in the eventual damping of the oscillations between the reactive elements. So these are some basics of the resonance circuit. So there are two types of resonance circuits will be there. The first one is series resonance circuit and the next one is parallel resonance circuit. So in this video we see about the series resonance circuits and associated derivations at all. So this is a series resonance circuit. I am already told that. So my coil has some associated resistance with it, so that it is represented by RL, and this is the resistance associated with the source. So only I put it as RS, and we add some resistance externally to the circuit to control the wave shape of the resonance characteristics. So in general the characteristics looks like this. So and I draw it. This is the normal characteristics. So in order to control the shape of this waveform, I add this resistance RD. So here these three resistance are connected in series, so that I combine these three resistance into a single value is called as R. So it is shown in the corresponding equation, so that my resultant series resonance circuit is shown in this figure D. Okay, so here in this loop I want to find out the overall impedance ZT. So this is the corresponding equation ZT, which is equal to R plus JXL minus JXC. So you take J outside. Okay, at resonance condition I am already told that the reactive energy absorbed by the element which is equal to the reactive energy supplied by the another element, so that this value of XL and XC must be equal at resonant conditions, so that it is applicable only at resonance condition. It is very important, so that my entire circuit will looks like it is a pure resistive circuit, because this XL and XC both will cancel each other, so that my entire circuit will act as a pure resistive circuit only, so that my total impedance is a TS, which is equal to R. This S indicates it is a series resonance. This T indicates the total impedance value. Okay, so that the total impedance which is equal to the R. So that I'm already told that at resonant condition XL equal to XC, I want to find out the frequency at which resonance should be occur. We know that the value of XL, which is equal to omega L, and XC is equal to 1 by omega C. Just you cross multiply this omega, so that omega square equal to 1 by LC. If I want to find out the value of omega S, take square root on both sides, so that omega S equal to 1 divided by square root of LC. This S indicates it is a series resonance circuit. Okay, so we know that omega equal to 2 pi F. So here omega S is there, so I follow the same notation, omega S equal to 2 pi Fs. So that Fs is equal to 1 divided by 2 pi into square root of Lc. So this is the resonance frequency, this is the frequency at which the resonance will occur in the series resonance circuit. Okay, here F is in frequency hertz, and L, the unit of L is Henry, and the unit of capacitance is Farad. So that the current through the circuit at resonance is, I'm already told that at resonant condition my circuit looks like a pure resistance circuit. So that in a resistive network we know that the current and voltage both are in phase. So that here they show like this. So there is no phase shift between my current and voltage, so that I equal to E divided by R. So the phase shift is 0 degree here. Okay, next the voltage across the inductance and capacitance are shown in this equation. We know that at resonant conditions XL and XC both are equal and opposite, so that the phase shift between these two voltages must be 180 degree, then only the addition should equal to 0. Okay, we know that in general V equal to I into X. Okay, if it is VL means it is I into XL, and it is VC means I into XC. So just I substitute these values, and we know that I here the phase shift of the current is 0 degree because it is in phase with the voltages, and here XL is 90 degree phase shift with respect to the current. Okay, so that if I multiply the my corresponding voltage across the inductance is I into XL at an angle of 90 degree. Similarly, the voltage across the capacitance is IXC at an angle of minus 90 degree. Okay, so it is explained in the figure. I am already told that my corresponding voltage and current are in phase, so that it is shown in the phasor diagram. So this is my supplied voltage E. Okay, and this is my voltage across the inductor, and this is the voltage across the capacitor, and I am already told that it is 180 degree out of phase, so that only it is phased like this opposite. If you add these two value, it will cancel each other. Okay, and this is the overall power diagram of the series resonance circuit. Here this diagram indicates the power it is absorbed by the inductive element, and this is the power supplied by the capacitive element. So both are equal and opposite direction. So if I add these two curves, it is entirely cancel each other, and this is the power absorbed by the corresponding resistance of the circuit. So this is the average power. So this diagram indicates how much the power will vary in the series resonant circuit. Okay, so the next important topic is the quality factor. So what is my quality factor, and for which I want to find out the quality factor? In general, the quality factor is to determine for the corresponding coil. Coil means the inductance which is used in the circuit. For example, consider it is a series resonant circuit. Okay, generally I want to find out the quality factor of this corresponding coil. Okay, so that the quality factor of the series resonance circuit is defined as the ratio of the reactive power of either the inductor or the capacitor to the average power of the resistor at resonance. Okay, so this is the explanation of the quality factor, and the another explanation is also there. So here there are two elements is there. So this element will store the reactive power, and this element will dissipate the real power. Okay, so the quality factor means how much energy is stored in the corresponding reactive element and compared to the power dissipated in the resistance. So this comparison is called as the quality factor. If the power dissipated is very less and the storage of the reactive power is very high, means the corresponding quality factor of the coil is somewhat high. So in general we choose the quality factor of the coil is as much as high as possible. For a series circuit in general, the quality factor is around less than 200. But in practical cases there are some limitations is that, because in practical cases each and every coil has some resistance inbuilt, so that automatically this dissipation of the power should exist, so that the quality factor is somewhat reduced. So in practical cases the quality factor of the series resonance circuit is around in and around 100. Okay, so here the reactive power is taken as I square into XL, and the average power dissipated across the resistance is taken as I square R. So just you cancel I square, and XL is replaced by omega S into L divided by R. So this is the quality factor. And if I want to find out the quality factor of the coil, means I substitute it is Q coil and it is represented by QL. It is XL divided by RL. Here RL is nothing but the resistance of the corresponding coil. Okay, so here I am already told that omega s is equal to 2 pi fs, and this is the resonance frequency. Fs is equal to 1 divided by 2 pi into square root of LC. We know that Qs is equal to omega s L divided by R. Okay, so therefore 2 pi fs into L divided by R. If I substitute this fs value into this equation. Okay, so that this L and this L cancel, so that remaining root L is present here. This 2 pi will cancel each other. Okay, so that the remaining equations looks like this. Qs is equal to 1 divided by R into square root of L by C. This is the another formula to find out the quality factor, in which only the element R comma L comma C is known. Okay, so in previous case it is omega L divided by C. If I want to find out the omega value, definitely my resonant frequency I want to know to find out the value of the quality factor. But in this formula I need only the elements of RLC in order to find out the quality factor. So depending upon the problem they specified, we use any one of the formula to find out the quality factor of the corresponding coil. Okay, so here the voltage across the inductance is shown in like that. So XL into E divided by Z into T. So we know that, so this is my series RLC resonance circuit. This is the R and this is L and this is capacitance C. So this is impedance XL and this is impedance XC and this is R. It is a series resonance circuit. Just you apply the voltage division technique. If I want to find out the value of VL here, and it is VC, so that VL, which is equal to, according to voltage division technique, the corresponding resistance divided by total resistance, the total resistance which is equal to ZT into the total voltage E. So we know that at resonance condition ZT equal to R, so that I replaced by R. Okay, so that this XL by R, which is called as QS. Okay, because we know that my quality factor QS is equal to omega S into L divided by R. Okay, here omega S into L is replaced by XL, so that this XL by R is replaced by the quality factor QS. And similarly, the voltage across the capacitance VC is defined as, which is equal to the corresponding resistance divided by total resistance into the total voltage E, and ZT, which is equal to R at resonance condition. So that this XC divided by R is also called as a quality factor. Okay, so that VCS, which is equal to QS into E. So these are the voltages across the inductance and capacitance at resonance condition. So next one, my total impedance versus frequency. If my frequency varies, how much the impedance varies? So from the corresponding derivations and graph, we conclude some important conclusions. So consider this is my total impedance Z equal to R plus J into XL minus J into XC. So just take J outside, so that Z equal to R plus J into XL minus XC. So the magnitude of the impedance is equal to Z equal to square root of R square plus XL minus XC the whole square. If I want to find out the impedance versus frequency, so that this equation is written in terms of frequency, because each and every element is a function of f, so that it is replaced like this: Zt of f, which is equal to square root of R of f the whole square plus XL of f minus Xc of f the whole square. We know that this resistance is independent of frequency, so that it is constant. So if I want to draw a graph for this equations, means if it is R, means it does not affect when the frequency will changes, so that my resistance is always constant when the frequency is varies. And similarly, if it is XL, means XL equal to 2 pi FL. Okay, so this 2 pi L is constant and F is the variable one. So this equation looks like y equal to mx plus c. It is a straight line equation, so that this equation is replaced by like this a graph. It is a straight line equation graph. And similarly, this xc is replaced by 1 by 2 pi fc. Just you cross multiply the frequency to the LHS side, so that xcf, which is equal to 2 pi fc. It looks like it is a hyperbolic equation. Okay, it is yx, which is equal to some say, it is looks like a hyperbolic equation, and the corresponding equation is drawn like this. So it is a individual response of each and every element in the corresponding total impedance of the series resonance circuit. It is an individual response, but I want to find out the total response, so that if I combine these three effects into the equation, then how it will affect the impedance, just see. Okay, so this is the hyperbolic equation, and it is due to the capacitive element, and this is the element which represents the response of the inductive element. If I combine this, so this is my overall response. Just see it. So this is the overall response, which is only I draw here. So at which point both curve will intersect, so this is the corresponding resonance condition. At which point both curve will intersect, that corresponding point is called as the resonance condition. Okay, so here this xc is predominant. So before that resonant frequency, this is the resonance frequency. So before the resonant frequency, for example, my frequency is less than f of s. Okay, and my f is equal to f of s, and my frequency is greater than f of s. So from this curve there are three different cases will be there. So look at this graph. When my frequency is less than f of s, means this xc is predominant. If xc is predominant, means my circuit will act as a capacitive. If it is a capacitive circuit, means we know that my current which leads the voltage E. Okay, and if f equal to f of s, means it is a resonance condition, so that xl and xc both are equal, so that my network looks like a pure resistive one. So this is a pure resistive network so that my current and I are in phase. So my current is in phase with E. Suppose my frequency is greater than my resonant frequency, means my circuit is predominant with X, so that my I current is lags with my voltage E. So this is explained here. So that if my frequency is less than my resonance frequency, my network is capacitive, which is greater than the resonance frequency means my network is inductive, and both the frequencies are equal, then the network should be resistive. It is explained in the corresponding graph. Okay, so next, selectivity. Select, just you see this graph. Okay, so see this graph. So this graph is inverted here. Just simply you see that graph is simply inverted. That means selectivity is the inverse of the frequency response of the total impedance curve, like that we say. So there is a definite range of frequencies at which the current is near its maximum value and the impedance is at some minimum value. We know that. See this diagram. So this is the resonant frequency. At resonant frequency, here my impedance is a minimum value which is equal to R. So that at resonant condition my impedance is very low. We know that my current I equal to E by Z T, which is equal to Z by R. So whenever my impedance is at minimum position, my current is at maximum position. Okay, so now you see this graph. Okay, so that at resonant condition my current is maximum value and my impedance is a minimum value. So that is given in the point. So here, so those frequency corresponds to the 0.707 or 70.7% of the maximum current, are called the band frequency or cutoff frequency or half power frequency or corner frequency. So this is the maximum current. Okay, so if I, in order to find out the selectivity, I go for some reference value. That reference value is called as the 70.7% of the maximum current or 0.707 I max value. So if draw the straight line, so in the graph there are 2 points which will cut in the corresponding graph. So this point is taken as F1 and this point is taken as F2. So this is my resonant frequency, and at this point the power should be only 50%, so that it is also told as half power frequency. Why it is 50%? So we should see in the next slide. Okay, so the range of frequency between the two, this frequency and this frequency, is called as the bandwidth of the resonant circuit. So that the bandwidth is represented by the difference between these two frequencies, F2 minus F1, or the range between these two frequencies is called as the bandwidth of the circuit. So half power frequency means, so what is the maximum power transferred? We know that it is P max. At half power frequency, only half of the power should be transferred in the circuit. Now you see, we know that P max is equal to I square max into R. I said it is 0.707 of I max. So substitute this value. If I square this 0.707, the resultant value which is equal to 0.5. Okay, so that here it is I square R max which is equal to P max, and if I square this value of 0.707, I get the value of 0.5. So that this 70.7% of the maximum current will give the 50% of the power, maximum power should be transferred to the circuit. Okay, and so from this figure, a small quality factor is associated with the resonant curve having a large bandwidth and small selectivity. Here, this range indicates the selectivity. If I want to select a exact or particular equipment. For the sake of understanding I say, so that if I want to select a exact element, then the selectivity is very necessary, so that this gap is as much as small, then the selectivity is greatly improved. Suppose the bandwidth is increased like this, it has a very long width, means then the selectivity is somewhat missing, so that whenever the quality factor is very small, automatically the bandwidth is increased, so that the selectivity is somewhat reduced, so that small selectivity is there. Suppose if I choose the coil whose quality factor is as much as high as possible, consider it is greater than or equal to 10, it is widely approximationly we used, so then the selectivity of the curve should be improved. Okay, and here there are two cases will be discussed. The first one is I fixed the L and C value and I vary the resistance, and in second case I fixed the value of R and I vary the ratio of L by C. Okay, here there are three curves will be there. If I increase the value of resistance, okay, automatically what we do, if I increase, automatically my bandwidth is increased, so that my selectivity is reduced. In other way, if I fix the value of L and C and I reduce the value of the resistance, automatically my selectivity is somewhat improved. Okay, so only we insert some external resistance to the series resonance circuit in order to obtain the particular wave shape. Actually these wave shaping circuits are used in the receiver side. For example, in radio receivers, we tune some circuit in order to select a particular channel. Okay, so in that case some L and C is fixed, just I vary the resistance, automatically I choose any one of the station. Okay, and similarly in second case, if I fixed the R value and I vary the ratio of L by C, then also my selectivity or my bandwidth is also varied. Okay, so when my L3 divided by C3 is increased, automatically the ratio, then the selectivity is increased for the corresponding curve. Okay, so this is the corresponding derivation in order to find the upper cutoff frequency and lower cutoff frequency. So in the previous graph we see two frequencies, f1 and f2. Okay, so here f1 is called as a lower cutoff frequency and f2 is called as a upper cutoff frequencies. Okay, so here I want to find out those frequencies. So this is the impedance value, is it equal to square root of r square plus xl minus xc the whole square, and we know that it is a half power frequency. At half power frequency we know that the current is around 0.707 times, so I equal to, we know that I equal to E by R. Okay, so that at this condition my current is reduced to 0.707 percentage from Imax value. If current is reduced, automatically my resistance is increased at the same percentage, which is equal to 0.707 up. So therefore my R is increased to 1 by 0.707 times. We know that this 1 by 0.707 is root 2, so that my impedance is increased from R to root 2 R when the half power frequency occurs, so that this ZT is replaced by root 2 R. Now squaring on both sides and you rearrange this equation, 1 R square and 1 R square cancel, so that R square equal to XL minus XC the whole square. So take square root on both sides and you rearrange this equation, R equal to XL minus XC or R minus XL plus XC equal to 0. Now you replace XL and XC is equal to omega L and 1 by omega C. So there are two frequencies there. First one is lower cutoff frequency and upper cutoff frequency. Here I want to solve for upper cutoff frequency, so that I put omega 2. Okay, and it is replaced by like this. So this equation is replaced by like this: omega 2 square minus r by l into omega 2 minus 1 by lc, which is equal to 0. And here I take l outside and I rearrange the equations in order to this value as positive. Why? Because means if it is a upper cutoff frequency, we know that in the diagram. So this is the frequency response characteristics. Okay, this is the impedance and this is the frequency. After the resonant frequency, the frequency is greater than resonant frequency, my circuit will act as a inductive one. Okay, we know that. So that only I consider this terms of positive, so that I just rearranging this equation. So this is the degree 2 equation. Just you find out the roots, so that we use the formula minus b plus or minus square root of b square minus 4ac divided by 2a. Now you substitute the values of this is the a, here a equal to 1 and b equal to minus r by l and c equal to minus 1 by lc. Now you substitute these abc values in this equation and you solve. The value of f2, which is equal to 1 by 2 pi into r by 2l plus 1 by 2 into square root of r divided by l the whole square plus 4 divided by lc. So here plus or minus sign is there. Here I neglect this minus sign. Why? Because if it is a f2 value which is greater than my resonant frequency, so that the negative sign automatically eliminated. Okay, so here I want to find out the value of lower cutoff frequency. Just follow the similar steps and you solve. The value of f1, which is equal to 1 by 2 pi into minus r divided by 2l plus 1 by 2 into square root of r by l the whole square plus 4 by lc. And we know that this r by l, which is equal to omega s divided by qs. Qs is nothing but quality factor. Just rearrange the equations. Okay, so that my bandwidth, which is equal to r divided by 2 pi l. Okay, just rl is there and just you rearranging this equation. That means just you multiply omega s up and down, so that here omega is there, here also omega is there. Omega l is replaced by xl and r is there. Appo omega l divided by r, which is replaced by 1 by qs. Okay, so that just you rearranging these equations, my final value of bandwidth, which is equal to fs divided by qs. So here just simply I rewrite this equation, so that it is omega divided by 2 pi into qs. Okay, and we know that omega equal to 2 pi f and f is equal to omega divided by 2 pi, so that this omega divided by 2 pi is replaced by f by qs. And if it is omega s, it is a series resonant circuit, just you substitute it is fs, so that bandwidth equal to fs divided by qs. And another way is just now you rearranging this equation. Just this fs is taken to the LHS side. We know that bandwidth equal to f2 minus f1. This fs is present here, which is equal to 1 by qs. So if the upper cutoff frequency and lower cutoff frequency and the resonant frequency is known, automatically my quality factor of the coil is also determined. So there are three different types of formula which will be available to find out the quality factor of the coil. By solving this equation, my resonant frequency fs, which is equal to square root of f1 into f2. So these are the corresponding graph for which VR, VL, VC and current for a series resonant circuit whose quality factor is greater than or equal to 10. Okay, so up to this I conclude. In next class we work out some problems on the series resonant circuit. Thank you.